Welcome to week 4 of our C++ track. This week, we'll be taking a look at concurrency and some of the tools the standard library gives us to manage asynchronous code. Concurrency in software happens when our program is working on multiple tasks at the same time. Sometimes we use this to make our program faster, when there's a lot of work to do that can be split into independent chunks. Other times, concurrency is needed to keep our programs responsive while waiting for external signals. Concurrency is what lets the buttons in your internet browser keep working while it's busy loading the site you just requested. Almost all robotics code depends heavily on concurrency to handle all the different algorithms and devices the robot is using. When our code is doing a task concurrently with other parts of our code, we can say that that task is asynchronous. When multiple tasks are being done one after another in a specific order, we call those tasks synchronous. You'll often see asynchronous shortened to async in symbol names. For example, functions that kick off some background task and then immediately return, leaving the background task running, commonly start with async as a prefix on their name. One way for us to model and manage concurrency is with threads. Each thread represents a flow of execution or a task being done by the computer. So far, we've been dealing with code that runs in just one thread, the main thread of our program. Everything in our code has been running one task at a time in a specific order. To do a task asynchronously, we could start a second thread and tell it what code to run. This other thread keeps track of its own position in the code and its own local variables. Thinking back to our discussion on the structure of our computer's memory, each thread has its own stack, but all the threads in our program share the same heap. And while threads manage their own stacks, all of the threads in a program have access to the entirety of that program's memory, so we can pass around pointers and references to stack objects between threads. All of this to say, while threads are running separately, they can still share some of the data they use with other threads in our program. Let's take a look at the life cycle of a thread. When our program starts, we always only have one thread, the main thread. When we want another thread, we create it. Any thread can create other threads, so this isn't something that only our main thread can do. When we create a thread, we get a handle to that thread, so we can manage its execution. In a way, the thread that does the creation owns the new thread. There are two ways to tell the computer that we're done with a thread: joining and detaching. To join a thread means to wait for the thread to finish executing, as in return from the top-level function we gave it. The owning thread that calls join gets blocked until the other thread is done. This is useful when we're waiting for some result that the other thread was calculating, or when we need to make sure the other thread is done before cleaning up some shared resources. To detach a thread means that we release our handle on it and let the operating system take over managing its resources. A detached thread can continue running as long as the process runs. We've essentially passed ownership off to the system to automatically clean up the thread when it's done. Detaching threads is less common, but still useful for background tasks that need to keep running for the lifetime of the program. Because we don't have direct control over the lifetime of a detached thread, we need to be more careful about what resources it shares with other parts of our code. Every thread follows this life cycle. It's created, runs for some amount of time, and is either joined or detached at the end. Now let's set up a quick example using the std_thread class in the standard library to manage threads in our C++ code. Here I've created a program that has two jobs to do. Each job takes 1 second to run. The main function is timing how long it takes to execute both jobs via the allJobs function. All we're doing here is getting the time before we call allJobs and the time immediately after allJobs returns. Then we take the difference of the two times to figure out how many seconds have passed. Note at the top we're including the thread header, which declares many of the standard library tools when dealing with threads. One of those tools that we're already using in this code is std_thisthread sleep4. This pauses the current thread for the given time. You may be familiar with sleep or delay functions in other languages. This is how we do that in C++. Now at this point, the allJobs function just calls job A and job B as synchronous tasks. They run one after the other, and our program takes about 2 seconds to execute. This makes sense because it has two jobs that each take 1 second. But these jobs don't actually depend on each other, so they could be run at the same time. Let's tweak the code to start each job in its own thread. And we can do that with the std_thread class. To create a new thread in C++, we just need to construct a new std_thread object and give it the function we want the thread to run. So we've got thread A, which will run job A, and thread B, which runs job B. Then we want our allJobs function to wait for all the jobs to complete, so we call join on each thread. The constructors of our threads will immediately return, and our main thread will get blocked on each call to join. Once the corresponding thread has finished, which happens when its job function returns, the join call will return and the main thread is unblocked. Looking at the output of our program, we can see that it now only took 1 second to run. Because each job is running in its own thread, job B didn't have to wait for job A to finish before it could start. Both jobs did their 1-second task during the same second. That's all it takes to manage a thread. Doing something useful with a thread is often more complicated, because you need to carefully manage shared state. If you don't, you can end up with something called a race condition, where the behavior of your program changes based on which thread modifies some shared object first. Threads are not the only way to manage concurrency in code, and complications like race conditions are why other tools are sometimes preferred for specific kinds of problems. Threads are often one of the key primitives used under the hood of these other tools though, so it's good to understand how they behave.